Hello and welcome to this course on the foundations of continuum mechanics. My name is Gaurav Bhutani and I'm a faculty member at Indian Institute of Technology, Mandi. These lectures are recorded as a part of NPTEL. This course on the foundations of continuum mechanics develops the mathematical and the physical foundations of continuum mechanics, which is essential to understanding both solid as well as fluid mechanics. This course emphasizes tensor algebra, stress and strain measures, conservation laws, and constitutive modeling. These ideas enable a deep understanding of the key concepts in continuum mechanics. This course is designed as a foundational course, and therefore it equips the students with the core concepts required for advanced courses such as elasticity, plasticity, advanced fluid mechanics, turbulence, and finite element method. This course also builds essential skills for computational mechanics, computational fluid dynamics, and finite element analysis. And these are key areas in aerospace, automotive, civil, and material industries. Most importantly, the focus of this course is on conceptual clarity. We also focus on mathematical rigor and a lot of problem solving, because our understanding is that it is through a lot of problem solving that the key mathematical and the physical foundations of continuum mechanics is reinforced. Continuum mechanics in general has got the tag of being a difficult course. However, it is not a difficult course. It is just because of the lack of understanding of the mathematical foundations dealing with tensors and the lack of understanding of the definition of key physical quantities is what makes this course difficult. Once you understand the definition of stress and strains, this course becomes quite easy. So in this course, we'll focus on the mathematical foundations and definitions related to the key quantities such as stress and strains. It is beautiful that the same ideas and equations that govern the motion of gases in rocket plumes, they also apply to the flow of rice grains in a hopper or to the deformation of a building under wind or structural loads. And the same equations are applicable to the design of aircrafts and automobiles as well. In fact, the motion of crowd or traffic is also modeled using the ideas of continuum mechanics. So here's the agenda for today's discussion. We'll be introducing the course along with the evaluation policy to you. I'll talk about myself and my teaching style. We will spend some time on appreciating the application areas of continuum mechanics to give you some motivation as to why you should learn this course. And towards the end, we'll talk about the definition of the word continuum mechanics and what the subject contains. So let's talk about some learning objectives of this course. We'll be spending a lot of time on the mathematics of tensors in the first few weeks, where we'll focus on the algebra and calculus of tensors. And the understanding of these mathematical quantities will help us with rigorous derivation and analysis of key measures which are typically encountered in continuum mechanics. We will be defining stress rigorously in this course. And then we'll be spending time on the kinematics of deformations and defining the key tensorial measures which are used for quantifying deformations of different types in continuum mechanics. Once we have a good understanding of the mathematics, the definition of stress and strains, we'll then talk about conservation laws, which are the key balance laws that help us write the equations of motion. And then we'll talk about constitutive models, which bring in the material specific properties into the picture. And in the very last week, to help you appreciate that whatever we have learned in this course is actually useful, we'll be applying these ideas to an actual fluid mechanics problem to solve it. Here's a detailed course structure. I'm not going to detail of each and every topic here in today's lecture. You can read through it in your own time. But as a summary, we have a total of 12 weeks of lectures in this course. And each week will have 5 videos that will be shared, where each video will be approximately 30 minutes in duration. And the last video of each week will be a tutorial where we'll be solving problems to help reinforce the topics we have learned in that week. The tutorial sheets will also be available to you over the portal. In this course, particularly, it will be the tensors that will be a new idea for you. And these mathematical objects called tensors, they form the language of continuum mechanics. Just like vectors were quite abstract to understand the first time you ever saw them, but with time and practice, they became a second nature, so will be the case with tensors. So I urge you to be patient and to keep practicing problems. With time, you will get comfortable with the idea of tensors. In terms of prerequisites, it is expected that you have been through a basic mechanics course, which is typically taught in first year undergraduate studies. You should also be comfortable with calculus of real numbers, vector calculus, and linear algebra. In terms of course material, there will be video recordings available as a part of this course. My lecture notes will also be available on the portal for you to go through them. And the textbook for this course is the book by Mace and Mace titled Continuum Mechanics for Engineers. We'll be using the second edition for notational purposes. However, a fourth edition is also available for your reference. Details of grading scheme and assessment will be available through the NPTEL portal, and I request you to please go through them in detail yourself. In general, there's an assignment every week which has problems from the topics from that week. And then there is one final in-person and proctored exam as a part of this course. Those who do exceptionally well in this NPTEL course will also have opportunities related to paid internships with us. This is a fully online course and all the material will be available through the NPTEL portal. You can communicate with us over the portal. However, feel free to provide any feedback or ask questions to me over the email address that is shared on the slide. We appreciate critical feedback anytime. That helps us improve the course and also helps you learn the course better. Please feel free to upload your questions over the portal, and while the course is running, I'll be replying to them every day. We'll also be conducting 1 or 2 live sessions per month for you to interact with us and the team and ask your questions if you have any. Transcripts in various languages will also be made available through the portal. Now, in terms of my expectations from you, the first and the foremost one is that you should enjoy the course, because if you enjoy the course, you learn it much better. And the other point I want to raise here is that the ideas matter. Sometimes we get lost in the equations and problems so much that we forget about understanding the key ideas related to the topic. I'll try to reinforce those ideas over time. However, please try to identify the key ideas in the various topics in this course. Please ask a lot of questions because peer learning sometimes can be very useful. So sometimes your question could be answered by somebody else who's enrolled in this course, and it will also give you a chance to interact with the others. Unless you're looking for a particular topic, I request you to watch the lectures in the right order. And most importantly, solve a lot of problems. It is only through solving problems that you can get comfortable with the technicalities of this course. Please complete assignments on time and please maintain academic integrity at all times. Here's a quick introduction about me. I hold a BTech and MTech with a specialization in fluid mechanics from IIT Kanpur. I worked in the industry for a couple of years, and these industries include metal mining, data science, and finance. Post that, I obtained a PhD in computational physics from the Department of Earth Science and Engineering at Imperial College London, and currently I am based at IIT Mandi since 2017 as a faculty member, and I also head the multi-phase flow research lab here. In our research group, we work on multi-scale and multi-phase flows, which include flows laden with particles and bubbles of various sizes. We work on modeling granular flows, particularly the dynamics of snow avalanches, and it is the ideas of continuum mechanics we apply for all these problems. In addition, recently we've been applying the ideas of machine learning, such as physics-informed neural networks and graph neural networks, which are deep learning methods, to solving the problems in mechanics. For our research, we use a lot of high-performance computing and supercomputers, where we develop computational codes from scratch and run these problems in parallel using CPUs and GPUs to solve the equations of continuum mechanics more efficiently. In addition to teaching continuum mechanics, I also teach courses in fluid mechanics, heat transfer, computational fluid dynamics, and high performance scientific computing. I'm passionate about this topic and also passionate about helping others learn this topic in depth and to be able to apply this for their research. Given the foundational nature of this course, we will be going really slowly in this course to ensure that you are able to understand each and every foundational idea in detail. And therefore, we'll be using blackboards for 90% of this course. Continuum mechanics is a highly interdisciplinary subject. It has applications in the area of mechanical engineering, aerospace engineering, civil engineering, material sciences, mathematics and biology, medicine, physics, and even computer science and sports science. Just to impress upon you the vastness of the application of this field, I have put in some application areas on this slide. We don't have the time to go through each and every application here today. However, please pause this video and have a look at the different application areas in this field. Let's now talk about what continuum mechanics is and why you should learn it. We must talk about mechanics first before we talk about continuum mechanics. Mechanics basically is the study of the motion of particles under the action of external forces. The discussion in mechanics always starts with the point mass theory. In this point mass theory, all masses are modeled as point masses. That means that the shape and size of the body does not matter. And this is typically taught in high school mechanics. If you recall that boxes, lifts, monkeys were all modeled as point masses to start with. You draw the free body diagram, find the net force, and equate it to mass times acceleration from the Newton's second law. The discussion on mechanics then moves on to rigid body mechanics, where the shape and size start becoming important. The motion then is split into the motion of the center of mass and the rotation of the body. This is where quantities such as the moment of inertia are typically defined. However, there's something more that is needed to complete the mechanical analysis. Real solid bodies, for example, they deform, and fluids deform continuously. And this deformation has to be quantified. So a plastic chair or a diving board will deform under the load when applied to it. So in continuum mechanics, we study the deformation or the rate of deformation of solids and fluids under the action of external forces and stresses. The word continuum comes from the Latin word continuous, and physical space around us is continuous. That is, between any two points in the physical space, you can always find another point. In fact, you can find infinite number of points between any two physical points in space. However, if we look at solids, liquids, or gases, there's a lot of empty space between molecules in them. So we can say that atoms and molecules fill the space discretely. So matter which fills the physical space is actually discrete and not continuous. So therefore, if I was to talk about a physical quantity like mass or density, technically it will be discontinuous in space, because there will be points in physical space where I'll have no molecule or an atom. That means that there will be no mass there, or I cannot define a density at that point. However, the scale at which we work, practically speaking, such as scales which are visually relevant, or for example, the size of a measurement probe that we use to measure quantities, these sizes typically are huge as compared to the size of an atom or a molecule. Although these sizes are still small, that is of the order of a few microns, but they are huge in comparison to the size of an atom. So the smallest practical scales we work with will contain billions of molecules in them, so that averages can be defined conveniently. So for our engineering analysis, we can assume that matter fills the space continuously, because over these smallest physically relevant volumes, which will have billions of molecules, we define quantities on an average. In fact, this idea allows us to define quantities at points. That is, we form a small volume around the point of interest, and we average the quantity for all the molecules in that small volume. So this is called volume averaging, and this is typically used for defining average quantities at points in mechanics. So quantities such as mass, density, velocity, acceleration, etc. can all be defined at points in space. So these physical quantities can be assumed to be continuous over space, as well as assumed to have continuous derivatives over space, which allows us to apply the mathematical operations to them while developing the theory of continuum mechanics. So let's say we want to define the density at a given point. So this is a point P. So what we'll do is we will take a volume around the point P, and this volume is going to be a small volume in the sense that let's say the length of this cube is around 0.01 meters. So that's 1/100th of a meter. That's really small. That's 10 micrometers or 10 microns. So in this small volume, I mean, we will never go below this volume in terms of engineering applications or physics-based applications typically. So, but in this volume, for example, if you're talking about air at standard temperature and pressure, this air is going to have of the order of 10 to the power of 10 molecules in this small volume. So that's 10 billion molecules in this very small volume. So we can easily define density as the ratio of the mass to the volume in this small. So the mass is the total mass of all the molecules that lie inside this small volume. So that's the limiting case, but we'll never go below this small volume for calculating quantities. So this method will allow us to calculate point functions, that is quantities, physical and geometrical quantities at a certain point inside the physical space. So this allows us to define these physical quantities continuously. In fact, even their derivatives will be assumed to be continuous. Now the question appears that can we apply the theory of continuum mechanics all the time? And the answer is no. For example, if you're defining a vacuum chamber, then by definition, a vacuum chamber is supposed to have very few molecules of air in it. So the idea of continuum mechanics does not seem to be relevant there. So in general, we should have enough number of molecules in a given volume so that an averaging can be carried out comfortably over small volumes to be able to define these quantities over points continuously. So it is a matter of scientific experience whether the theory of continuum mechanics is applicable or not. However, there are some quantities which help us with the fact whether the theory of continuum mechanics is applicable in that condition or not. One such quantity is called the Knudsen number, which is named after the Danish scientist Knudsen. So the Knudsen number is defined as the ratio of the mean free path to a characteristic length. So mean free path inside this small cube containing molecules of air is defined as the average distance a molecule travels before it ends up colliding with another molecule or with the walls. So this is going to be tiny, the mean free path in this case, because we're talking about 10 billion molecules which are enclosed inside this small volume, which is 10 microns by 10 microns by 10 microns cube. So this ratio of lambda to L in this case can be considered as the size of one of the sides of the cube, which is 10 microns. So in this case, the Knudsen number is going to be much smaller than 1. So we can say that the Knudsen number is much less than 1 in this case. So in this case, we can apply the continuum hypothesis. In fact, typically we would say that if the Knudsen number is less than 0.01, then the continuum hypothesis is valid. But again, this is a matter of scientific experience. This number is not 0.01 is not cast in stone. There are situations where the Knudsen number can be of the order of 1, such as in the case of rarefied gases. So in that case, we cannot apply the continuum hypothesis. So with this now, we are ready to jump into the world of continuum mechanics. In the next lecture, we'll be starting with the mathematical foundations of tensors, which form the language of continuum mechanics. So thank you very much and see you in the next lecture.